I'm Roshan, recording experiment 7 that I'm running now. So this experiment is about support vector meshing, and let's see. So here we need three packages. One is E1071, one is Gmom, and one is Ketos. So E101 is for the function SVM, and Gmom is for the specific function to check the accuracy of the SVM model we created. So let's see. First, we import all the packages that is required. So we have this, and we have the other two also imported. Then we're going to use the dataset which I have called glasses, and we're going to import the dataset. It's going to be inside a variable called dataset, and you can see the dataset here. So this is the dataset. It has attributes called RINAMG. It's all basically those are chemicals, the amount of chemicals used in that specific class. And if you plot the dataset before it is being classified, this is how it is. So let's see, we're gonna apply a scheme and we're gonna use the function linear. If you look into the documentation of SVM, let's see, the kernel argument can take a number of different values called linear, polynomial, radial basis, sigmoidal. These are the methods the functions to be you want the function to be performed on. How you want it to be performed, and here we're going to use linear, so we're going to run that. You can see the summary of the model and what are the components of the model using the names and summary function, and you can see this is a summary, and here it says the number of support vectors. The number of support vectors should not be as many as the number of instances provided. If it is, that means it's a bad model. So basically what it is telling is it's using all the instances provided to create the model. So if it is like that, it's not that great, and it shouldn't be 2 less 2. So it should come an average value. It should be yeah, that's always a good. This is an okay value for the number of instances we provided, and this is a summary. And here it says all the kernel we use, the course, the gamma value, and the number of classes, and we have levels of A, B, C, D, E, and F. After that, what we're going to do is we're going to float what we created. So we're going to float that model on the dataset called dataset, and we're going to try to figure out SI, the value of SI using the attribute C. This is a formula you could actually plot it using a number of different attributes, but it's going to increase the dimension of the plots. This is the result we got. And now we're going to try to predict, and for predicting here we're going to use the dataset again. So you create the model using the entire dataset, and you're going to predict the entire dataset with the model create. So this is what we're doing. We're going to use the model, and then we're going to apply it on the dataset. Then we're going to predict, and the predicted values will be on a variable called predict. And we're going to create a confusion matrix. So the confusion matrix is like it gives an idea of the error or how good was the model actually in real. So let's see the table that is created. You can see the table, all the diagonal values are what we need, and all the other values are the error. So A and A came right 49 times, and when it was A, it was set it was B. It was predicted to be B 21 times. That's a big error. And when it was B, it was predicted A 16 times. So that is another error. So what we're trying to do is find the error. So we're going to type all the values which is outside the metric, outside the diagonal. So we use the technique 1 minus sum of all the diagonal values in the table by the sum of all the values in the table, and we're going to get the mean class error. So let's see the mean class error in our generated model. Mean class is an error of 0.28, which is not so much, and we're going to check the accuracy of the model using the accuracy function. And let's see, we have accuracy in 0.7 1495, which is good. And that is all. Thank you.